How do you like the theory part of this class so far? Not too bad, huh? People sometimes start their machine learning class with a theory, which I think is a big mistake, because then it's like, why are you telling me all these things? I don't care about them. Hopefully at this point we actually have met enough of the algorithms and the problems that we can see where these things might be useful. Okay? So, but now let's get to more theoretical theory. Right? Bias invariance, is still sort of like a pretty practical kind of theory. Right? But now let's get even more theoretical. But there's a reason why we're going to do this. Is like we're going to see something amazing. Right? So, and this is the notion of PAC learning, right? And it must be amazing because it won Leslie Valiant the Turing Award, right? They don't give out Turing Awards for just anything, right? So PAC learning is actually an attempt to answer these fundamental machine learning questions that always come back to haunt us when we're doing machine learning in practice. Like, for example, overfitting. Why does overfitting happen? Overfitting happens because what I care about is the generalization error, but what I can see is the training set error. If those two things were the same, machine learning would be easy, or at least no harder than many other combinatorial optimization problems, let's say. Okay? So the question for us is, can we infer something about the generalization error just from looking at the training error? PAC learning is a way to answer this question. Right? You can see how powerful this might be, right? What I want to do is just by looking at the training error, being able to say something about how well my learner is going to generalize, right? Clearly, good answers to this will have a big practical impact in, the design of classifiers and whatnot. And indeed, as I mentioned, support vector machines come out of this theory. Okay? So this is one question that we're going to be looking at now. The other one, of course, is this perennial question: how much data is enough data? Should I gather more data? Or, these days, I do have these bazillion examples sitting on disk, but should I burn more cycles trying to mine more of them? Right? Should I be just satisfied with a random subset of 10,000 of them, or do I really want to go to 1 million? Right? Is there a way to answer this question, or do I just have to painfully find out by trying? And then, even if you did 1 million, what if you went to 1 billion? Can I be sure that I don't need to go to 1 billion? Right? We would very much like to be able to answer this question, right? So, the other thing that we're going to be trying to figure out here is how many examples are enough? Can I have some sort of a priori estimate of how many examples I'm going to need to use in training in order to guarantee that I have, pretty good generalization? Okay? So what we're going to look at here are answers to these questions. So as usual in theory, let's start with a few definitions, but these are definitions that we mostly already know. So I'll go through them quickly. X is my training set, a bunch of instances. H is the set of hypotheses that I'm going to consider, right? So the mission of my learner is to pick one of these hypotheses and tell me, I believe this is the truth, or as close as I can get, okay? There's a set of possible target concepts C, which is not necessarily the same, right? Your concept came from some set of concepts, and there's the set of concepts that your learner is looking at. They might be the same or they might not, okay? So I'm gonna call the set from which my target concept comes C. Okay? And now, I'm going to assume that my training instances are generated by a fixed probability distribution on the instance space. Right? I'm going to randomly generate email messages, right? By randomly, sticking words into them. And they might or might not be spam. Okay? I'm going to call that distribution curly D as usual. Right? So this is a distribution over my instance space without the labels. Right? So I have a distribution that generates a message, and then later I'm going to generate a class from it. Okay? But the distribution, the important thing to remember in what we're going to be doing here is that the instance is generated randomly, but then the class is deterministic. Right? We're not in here going to look at the case where this instance 80% of the time is positive and 20% of the time is negative. We can handle that case in general, but here we're just going to stick with the simplest case. Okay? And so now what the learner does is it sees a sequence of training examples C and examples X, C of X, where C is the class of X. Okay, and of course this came from my target concept C, which is a member of my set big C. Okay. So the instances come from the distribution D, and then the teacher, right? We have a teacher that says, oh, the label for this instance is C of X. Okay. Any questions? This is all straightforward. Okay.
Could you please explain what you mean by concept?
One more time?
Could you explain what you mean by concept, the C, the big C?
No, again, a concept, remember, a concept is just a binary class. Well, when the function that we're trying to learn is binary, we call it a concept. When it's Boolean, right? A concept is just a Boolean function, right? Every time if you prefer, everywhere you see concept, just think Boolean function, right? Concept is, this is a tree or this is not a tree, right? A multi-class problem would be classify this into tree, shrub, grass, animal, etc., etc. Okay? Again, for simplicity, we're just going to consider the binary case, and that's what we call concept. Okay?
So is the classifier, like classifier outputs? Like
the classifier is your hypothesis, right?
Okay.
So the classifier, if it's a concept learner, right, is also going to output 0 or 1. The whole question is, how does that function relate to the real one, right? So the classifier produces a Boolean function, right, a concept, and the real concept is also a Boolean function, and we would like the two to agree as much as possible. Okay? All right. So the learner is going to output a hypothesis H, which hopefully is a good estimate of the real concept, the real Boolean function C. Okay? And the way we're going to evaluate H is by seeing how accurate it is on future instances from curly D. Right? And again, my instances are chosen probabilistically according to D, but then my classes are given by the teacher deterministically. Okay? This is just, stating in summary form the setting that we've been in all these weeks. Okay? All right, so the true error of the hypothesis, which is what we're really interested in, right, is the following, right? Let's suppose that my instance space is this rectangle, right? So we're going to use our good old stalwart, the Venn diagram, right? This is my X. And let's say that my concept C, my true concept C, is this ellipse, right? Inside it, you're positive, and outside it, you're negative, okay? My hypothesis, however, is this ellipse, right? Which means that it's right some of the time and it's wrong some of the time, right? Where does this hypothesis make errors? In these two regions, right? In this region, the true answer is plus, but my hypothesis says minus, right? And in this region, it's the opposite, right? The true hypothesis is, the true class is minus, but the hypothesis says plus, okay? So the true error is basically the sum of these two areas. Although in generally, what we have is a distribution, so it's basically the sum of the probability mass that's piled up on those two areas that I hatched, okay? So here's the definition. The true error of the hypothesis, error sub curly D, is the probability over all the instances in D that the class is different from the true class is different from the predicted value from H. Okay? And notice this, so this is an expectation computed according to the probability distribution over the instance space. Okay? Everybody with me? Very good. And now, of course, we have two notions of error. Training error is the probability that H differs from C on training instances. Okay? And the true error is the probability that H differs from C over future instances that are chosen at random from curly D. Okay? And what I'm really interested in here is the relationship between these two. So I would like to bound the true error of H given the training error of H. Okay? So I've seen how often H differs from C on the training data. I want to estimate how often it's going to differ from C on the data that I haven't seen. Right? That's the goal here. But to simplify things further, let us first consider the case where I'm able to get to perfectly fit the training set. Okay? In general, you might not be able to do that, but with a sufficiently powerful learner, like say a decision tree learner, I can always do that, right? Just basically by memorizing the training examples, right? So let us for now assume that we are able to do this, right? So I have a learner that is able to perfectly fit the training set, meaning my training error is going to be 0. But of course, the real error, the true error, might not be, and that's what I want to figure out. Okay? Questions? Version spaces. Remember when we defined version space? The version space is the set of hypotheses from my original hypothesis space that are consistent with the examples that I've seen so far. Right? When I see a new example, I throw out all the hypotheses that make the wrong prediction for it. And on an ideal day, at the end of the day, I have one hypothesis left in my version space, and that must be the true one. On a bad day, I have 0, and I must change my hypothesis space. On an okay day, I actually have a whole bunch of hypotheses, and then I need to, randomly choose between them or average them or something. Okay? So here's a graphical illustration of this. Each of these points is an instance in the training set. So each of these is a training example, right? And my Venn diagram now is my hypothesis space. Right? So each point on here is a hypothesis. Okay? And I'm labeling each point with both its true error and its error on the training set. Okay, I'm calling the error on the training set R. Okay? So for example, this hypothesis here had an R of 0.4, right? Which means it's not in the version space, right? The only hypotheses in the version space are the hypotheses for which R is 0. So this line here is meant to include all the hypotheses whose error on the training that is 0, and that's the version space. Okay, so this here is the version space. Okay. And now, truth in advertising. I'm not going to be able to predict what the error of my hypothesis on test day is going to be. This is too hard. What I'm going to be able to do, though, is to put a bound on it, which is not bad. Particularly if that bound is low, this is pretty useful. If I can guarantee that, the generalization error of my hypothesis is at most 10%, that's something to be pretty happy with. Okay? So the question for us, stated a little bit more technically, is what is the highest error among the hypotheses that are in the version space? Okay? I've seen a bunch of examples. I have this many hypotheses left in the version space. They all have training error 0, right? Because otherwise they wouldn't be in the version space. And my question is, what is the biggest error among those hypotheses? Right? Because I know that whatever hypothesis I pick from the version space, then its error is never going to be bigger than the worst one. Okay? So if I know what that worst error is, I have a bound on the true error of the hypothesis that I'm going to return at the end of the day. Okay? Everybody clear so far? Very good. So